Let's go and take a look at lesson 3.7, the derivatives of inverse functions. This section starts with kind of showing you the relationship between a function and its inverse. And you have to remember an inverse function is like the undoing of the original function. We have a pattern that describes the relationship as you have an x and then it produces a y. And then many times in mathematics, we like to work backwards, and that's what the inverse function is. It's the rule for working backwards. And many times we apply inverse operations when we solve equations. And so you're familiar with that. And it's just a reminder again, the power and why we care about inverse functions. Many times we want to know how to work backwards. And so what you see here is a formula for the derivative of an inverse function. Now, I'm going to let you know up front that many times it's easier just to calculate the derivative in a normal way versus applying the function, I mean the rule. And so it's just important to think about there is a relationship. So here's your original function, and then you have the inverse. Remember, the relationship is that they're reflected about the y equals x line, that relationship. That's the graphical relationship. So if you're looking at derivatives, right, which are the rates of change, right? So we have the relationship between x going to y, and we know its derivative, its rate of change. It'd be interesting to know what is it going back, what's the derivative. You see there's a reciprocal relationship between those slopes of the tangent lines at various points. And that's what gets us kind of to this reciprocal here. But again, I wouldn't focus too much on learning and memorizing this here. The applications really occur with the trig functions, right? The inverse trig functions, which are utilized in trigonometry and utilized when we solve physical problems involving trigonometry. So it's important to know the derivatives of those functions here. You can apply it, but sometimes it'd just be easier if you know what the inverse is, just then here's g of x, right? And the inverse, just take the derivative of that and don't apply the function. It's up to you. I wouldn't emphasize this too much, but you can apply if it comes naturally to you or quickly to you. I think the big emphasis, right, as you can see, is I just want to again show you one more. You have that, and once you know what the inverse is, it's easier just to take the derivative of the inverse versus trying to apply the function in many of the cases. We continue on before we get to the trig functions, the rational exponent power rule. So even if you don't have, and this occurs again because you will see x to the 1/3, x cubed, right? You have these rational functions start to emerge when we find inverses of power functions, that we then can extend the power rule for rational exponents. So it doesn't have to be integers, right? You can extend it and it works the same way, right? Finding the derivative of that. You can see 2/3 x to the negative 1/3. And you get good at subtracting fractions quickly, being able to go from, when I subtract 1, that's 3/3, right? And that's where the negative 1/3 comes from. So you want to be fast with these rational, don't let these functions, fractions mess you up as you do that. Okay, now I think the next place is kind of the memorizing of these rules here and realizing that the -1 does not mean exponent, but it means inverse functions, right, in these cases, and that these become the rules that we use. And again, mostly the ones we memorize are the sine, cosine, tangent, in terms of being able to remember that. Now, there are nice proofs of where those come from, but right now we're just going to apply them. And of course, like I've said before, math majors may be interested in the proof, but here's again an example of calculating that, right? It works the same way, will be a chain rule or a product rule, right? It's just these formulas are getting applied. Those are the derivatives of this. So you can see an example here. You know what the derivative of tangent x is, right? And now we're substituting, now you have an x squared in there. And so then you can see that. Again, this is where I like that of using the U notation. U notation seems to work better here when you're trying to take derivatives of chain rules. Like U notation works, like let U equal x squared, and then we know the derivative of tan negative u is 1/1 plus u squared, right? And then times the derivative of u, like using that u substitution becomes important. So I just want to highlight those here, and again, you can see those solutions again as you see, as we take the derivatives, this turns out to be a product rule, right? You have a product rule here, 2x times this plus the derivative of this here. You would see on this problem here, as you take the derivative of the inverse cosine, we don't have a product rule in this case. That one would be a chain rule, only a chain rule on this case. Can't get my pen to work, so I can demonstrate this one. There we go. So what we now know is, let's get to what is the derivative of inverse cosine, right? It's -1, right? -1 over the square root. So we're going to take the derivative inverse cosine -1. It's -1 over the square root of 1 minus x squared, right? So let's go ahead and do that one together real quick here, just to show you the application of the chain rule there. Let me make sure to get my pen working this time. There it is. So when looking at this here, I'm going to let u equal 3x minus 1, which then I know the derivative of u equals just 3, right? So in this case, now we have h of x equals inverse cosine of u. And so we now know h prime of x is equal to, we're going to take the derivative of this. So the derivative of this is -1 over square root of 1 minus u squared times the derivative of u, right? And so now in this case, that just leaves us 3 over 3 times -1, -3 over 1 minus square root of 1 minus 3x minus 1 squared. And then that would be your derivative there. So you could pause it. Sorry for a little sloppiness there, but that's what we're looking at there and how you apply that. Let's see. I think that's what I want to highlight from this section, being able to do that. You get some problems here, be able to do that. That's it.